Hello, my name is James Baski and a graduate student of Memorial University. Today I'm making a presentation on the design of an adaptive neo-fuzzy influence system, or ANFIS for short, for a boost converter. As we all know, boost converter is basically a step-up converter for power electronic systems. Now, let's take it to the layman's understanding. Usually, if you require a power supply, okay, of let's say 20 volts, and you have a 12-volt supply, what do? This is where the boost converter comes in. You are able to design or implement a step-up converter to step this voltage up from your 12 volt to a 20 volt. And this can be done by putting together some power electronics or electronic elements to be able to boost the voltage up. Now, like I explained in the layman's term, in order to achieve the stepped up voltage, we are working with three prepositions. The first has to do with an open loop boost converter. Now, it is basically made up of a MOSFET and a diode, which is coupled to a capacitor, and we have the output resistor. But then you have an inductor connected to the input. So from this circuit, we understand that we have two elements, storage element, that's an inductor and a capacitor. And there's a MOSFET that mostly does the switching. Now in figure 2, what we are going to do basically is to reconfigure the open loop circuit into a closed loop circuit. Then we incorporate a control system. So the output of the open loop is then fed back to the switch. And this is to improve the output, feed the output back to the switch. And so we have, some corrections so we get the desired output. Here in our project, we have a 12 volt and we want to attain a 20 volt through these three processes to see which gives an effective result. Now the third one is, after we run the closed loop using a PID controller, we are going to retrieve that data used from the tuned PID controller, and we will use that data to train the ANFIS controller. The aim is to get something close to what we have from the PID, but to be able to fine-tune the output result by the fuzzy logic controller. And that is why we are using data collected from this. And we used over 200,000 input data from the PID to train the ANFIS controller, or the fuzzy logic controller. For the open loop or the boost converter circuit, it operates this way. Now, when the MOSFET is switched on, the voltage across the inductor conducts to ground, and the diode, which in turn opens the diode, behaves like an open circuit by the diode. The diode behaves like an open circuit in this situation. So during phase 1, when the MOSFET is switched on or is closed, current flows to the inductor. This inductor stores energy in the form of a magnetic field. Now, once this thing is closed, because of the connection to ground, the diode is in turn reverse biased, so current doesn't flow through the entire circuit. However, when we switch the MOSFET on, when we open the MOSFET, when we open the MOSFET, current now flows through the system to charge the capacitor, and in turn flowing through the load. Now, the stored energy in the conductor is then transferred to the capacitor and to the load. In this case, the diode behaves in a forward bias manner, and it allows current to flow. So this process repeats over and over within microseconds, during the switching process of the inductor. Now, at the load side of the second figure, at the load side, because the inductor stores energy or charges, the voltage across the capacitor plus the voltage from the inductor, which flows through the load, causes current which is greater than the initial 12 volts that would have gone through the circuit initially. So you realize that at the load side, you have V0 becomes VC plus the current from the inductor, VL. By so doing, we have voltage magnitude greater than the V in, and this logic would give us a boost converter, because then the output becomes more than the input. So like I said before, for a PID controller, we used the open loop controller. However, we connected a feedback for us to gain a proper feedback, or to get the desired feedback. For the ANFIS controller, like I said again, we picked information from the PID controller, fed it to the ANFIS. Then we trained the ANFIS using MATLAB Simulink, Fuzzy Logic Designer app to train the controller. And by so doing, we're able to optimize the voltage output from this design. And from the simulation results, we will understand how we're able to improve that from all three scenarios. Now, from the simulation results, the output we're requiring was 20 volts from an input which is 12 volts. And from the open loop, we couldn't attain the 20 volt output at all. We couldn't attain this required output. However, for the PID controller response, we were able to achieve 20, but it was slightly above the required voltage. And in this sense, if we are powering a sensitive equipment to this controller based to the PID based controller, we would have issues with voltage regulation. So we didn't get we got what we desired by was slightly above the voltage. It was in excess of 20, almost 21 volts. Meanwhile, we needed 20 volts. For the ANFIS controller response, we realized that after the simulation, we got an output voltage of 20 volts, exactly 20 volts. And I could say that this is because of the data we took from the PID controller, And the ANFIS was able to fine-tune the voltage from 21 volts to 20 volts, which was specifically what we needed for our work. And during the simulation, we also we took the response, or we were also interested in the response for the voltage and the diode current. We're also interested in the voltages across the MOSFET and the capacitor. So all these were plotted and realized that the voltage or the waveform, the theoretical waveform, and the waveform generated from our oscilloscope or our scopes were in sync, were correct, were in line. So it tells us that whatever we were doing, we were on the right path. Now, in terms of analysis of the results, both controllers were subjected to a 12-volt DC input. However, the output for after the simulation, we realized that the open loop controller, boost controller, was giving us 18.83 volts, whereas the PID based boost converter was giving us a 20.99, which is approximately 21 volts. And we didn't really want anything above 20, because whatever we were going to power, whatever output, we were going to subject the output to a very sensitive equipment. So we didn't need anything above 20. However, the ANFIS based closed loop based converter gave us 20 volts, and that is probably because, one, we picked data from the base control and the PID based controller, and the ANFIS was able to fine tune the results for us to attain the required 20 volts. Furthermore, we subjected our simulation to OpenRT and a hardware in loop simulation or hardware in loop validation. And through the validation, we were also able to achieve the 20 volt output that we were reading from the ANFIS based controller. So we're able to fully validate whatever outcome it was for the ANFIS controller. And we can clearly state that the research or the design we did was successful, as the output required was attained. In conclusion, we can say the ANFIS controller's ability to dynamically regulate the boost controller's operating makes it a powerful tool, and future research would have to be developed for a much more complicated systems. This is a base system. This is a simple system, but if it could work for a very simple system, we have no doubt that it could work for a much more complicated power converters. Thank you for giving the time. I would use